Hello, in today's video we will speak about gradient coil simulation, and we will use Magpylib Python library to parameterize the gradient coils, visualize them, and do parametric sweeps of different variables to understand their effects. So what are the objectives of the video? First of all, the video has some prerequisite knowledge requirements. A basic understanding of MRI operation is assumed for this video. And the main objective of the video would be understand the physical necessity of gradient magnetic fields in the X, Y, and Z directions for spatial encoding, explore the design, geometry, and construction of practical gradient coils, learn how to effectively implement parameterized coil definitions using Python, perform magnetic field simulations and create 3D visualizations using Magpylib library, and finally conduct parametric sweeps of different variables to analyze their specific effects on the magnetic field. So let's start with theoretical foundation. First of all, human body is composed of roughly 60% water, and water in its turn has oxygen bounded to 2 hydrogen atoms, so it has an abundance of protons. And proton, it has a spin quantum property, and under applied magnetic field it does a special motion called precession, which resembles to spinning top, and that precession can be quantified using Larmor frequency, which is the resonant frequency of a spin within a magnetic field of a given strength. This frequency is proportional to magnetic field, as we see from the equation, and the constant of proportionality is the gyromagnetic ratio. It's important to understand that the gyromagnetic ratio is intrinsic property, which means that it's constant. So the only way we can change the frequency of resonance is by changing the magnetic field. So if we compare two fields, let's say the weak field with a strong field, weak field will cause lower frequency, while the strong field will cause faster frequency. And let's understand why we need the gradient. In MRI, let's take 1.5 Tesla scanner, and gyromagnetic ratio of hydrogen atom is 42.58 megahertz per Tesla. So when we use the equation we just showed, we get that the Larmor frequency, or the resonant frequency, is 64 megahertz. It means that all the protons inside our body are precessing with the same frequency. So if we take a proton from, let's say, toe, we get the same frequency. If we take from leg, we get the same frequency. From the body, we get the same frequency. From arms as well. And by this, we see that we have the same frequency all over, which means we have no spatial information. Basically, although we have the strong magnetic field, this field itself can't be used alone to get spatial information. So what we need to do, we need to change the frequency somehow to get spatial encoding. And as we showed before, the only way to change the frequency is by changing the magnetic field, because gyromagnetic ratio is intrinsic property which we cannot change. So how the gradient field is achieved? Let's see the gradient fields in Z direction. Here we activate our two coils, which resemble Helmholtz coil, but unlike the Helmholtz coil, the currents are in opposite directions. As we can see from the right-hand rule, the right one, which is the additive field, produces a field which superimposes positively on top of the main magnetic field, so it increases the field on the right side. And similar and opposite way, the left side is a subtractive field. So now on the left side we get 1.5 Tesla minus Bz, and on the right side we get 1.5 Tesla plus Bz. What this gives us is that now from left to right the frequencies would change, or they will increase because the field is increasing. So now if we compare the frequencies of precession, we will see that we are getting increasing frequencies, which now gives us the ability to do slicing in Z direction. So different frequency gives the ability to select slice. But selecting the slice is not enough. Within the slice, we still need to localize our signal in X and Y directions. For this, I would highly recommend to check out the source cited in the slide, where you can find more information about the specific encodings achieved, but Y gradient in general is called phase encoding, and X gradient is called frequency encoding. So when they both are applied within a given slice, so within a given slice we mean that Z gradient is already applied. Now we have phase encoding on the y-axis, which means that the upper spins have a different phase than the lower spins. And we have frequency encoding on x-axis, which means the left spins and the right spins have a different frequency as well. So now we can fully localize the signal in 3D. Now let's look at the structure of gradient coil. So as we discussed, it has X, Y, and Z coils, and the Z coil is the simplest, which is a Maxwell pair or Helmholtz coil with opposite currents. Y and X gradients are composed of saddle coils, and this is the most basic design. The design can be further complicated to create more homogeneous or stronger fields, but this is the foundation. So now let's see step by step how we can create the Y gradient, then the X gradient, and then the Z gradient. So the first step in creating the Y gradient is to create a base saddle coil, because as we see here, the Y and X gradients are composed of 4 saddle coils, but each of them itself is the same. So we create the base saddle coil in the first step with given radius, length, and alpha, which is the angle. The alpha can range from 180 degrees to 0, but 0 is impractical, so let's say like 30 or 40, but usually it's around 120 degrees with given length, radius, and alpha. It's important to note that the base saddle coil is centered around the origin, but to get the gradient field we need to translate, rotate, and mirror the base gradient coil. So that's why in the step 2 we define a translate function which takes an coordinate array in shape of n by 3 and also takes the input of desired xyz coordinates we want to shift the center, and the vector is being defined as the input desired coordinates, and then the array is summed with the vector and the array is returned, so we get translation. In this case we use translation up. Similarly we will use translation down, but for translation down first we need to mirror the saddle coils, and here the parameters we use in translation are defined from separation and distance. So here we already got 2 coils, and in order to get the remaining 2 coils we need a mirror function. So what does the mirror function do? It takes the array, which is again the array of the coordinates of the coils, which we want to mirror, and it takes the input plane, so on which plane we want to mirror the coordinates. So the plane can be yz, xz, or xy, and mirroring is defined from linear algebra. As you can see, we just multiply by a corresponding vector and return the array. And again, after the mirroring, now we have the Y gradient ready. And from the symmetry, we can note that once we have the Y gradient, it will be really easy to have the X gradient. We just need to do 90-degree clockwise rotation. So that's why we define a function rotate. And again, from linear algebra, we have the rotation matrices for different axes, so for x, y, and z. So the function takes those inputs, the array and the rotation axis, and multiplies with the corresponding matrix and returns the array, the rotated array, which in this case is the x gradient. We will see all of this in the code, and the code will be available in the description below. The Z gradient, as I said, is Helmholtz coil with just opposite currents, and to get more information about Helmholtz coil, I did a video about that, so feel free to check that out, and the GitHub code is in the description of the video. So then, after we'll make the fields, we'll visualize them to make sure that they behave as expected. So as we can see, X gradient, Y gradient, and Z gradient increase their magnetic field correspondingly with X, Y, and Z axis. Then after we are done with visualizations and make sure that everything works as expected, we will do parametric sweeps. So we'll study what changing alpha does to our fields. Then we can also do nested parametric sweeps, so we can study combination of multiple variables. In this case, we see parametric sweeps of different combinations of separation and distance. And finally, we will be able to do nested parametric sweeps, which will take two or multiple variables and study the combination of them. So now, after we understood the whole procedure, let's go to Jupyter Notebook and see the Python implementation of our gradient coil simulation. So now we are in Jupyter Notebook, and let's start by importing the main libraries we'll need. So here are the functions which I spoke about. So here we have the translate function, the mirror function, the rotate function, and here I grouped everything to create the XY gradient into a single function, which just takes radius, length, alpha, distance, separation, and the current as inputs, and returns the X coil coordinates, X gradient as Magpy object. So this is a magnet. Y coils coordinates. So by coordinates I mean they are in shape n/3. And Y gradient, which is again a magnet. So how we do this is first we parameterize the arcs, which is done by creating a variable theta, which goes from pi minus alpha over 2 to alpha plus pi minus alpha over 2 in resolution number of steps. The resolution will be hard-coded globally in order to avoid shape mismatches and to be consistent within functions. So the rest is simple parameterization of a circle. So x, y is r cosine theta and sine theta respectively, and z is array of zeros with resolution number of elements. So why it's like this? Because initially, as we showed in the presentation, the base saddle coil is centered at the origin. That's why the z is 0 at the start. So then we define the first arc, which is by stacking xyz coordinates. Then we define the arc 2 by translating arc 1 L over 2 in z direction, and then we translate arc 1 back from the origin by minus L over 2. So the distance between them would be L. Then we define the point 1 and point 2, which are the first points of arc 1 and arc 2, which we then just connect using the linspace function, or we can just simply have them in an array. Why I have the two equations for the same L1 is because for visualization this produces a better results, like we get more points. But for Magpylib, this is more than enough. We just need the 2 points to define a line. So for Magpylib, I will just comment this part. But for general visualization, I will comment the bottom part. So now let's comment the bottom part, because we'll first visualize, then use the Magpylib. So then L1's coordinates are vertically stacked version of the L1 which we just defined. Similarly, point 3 and point 4 are the first points of arc 1 and arc 2, which are again connected together with line 2. And we have two definitions for line 2 with linspace and just ordinary array of 2 points. So for now I will comment the 2-point version. And finally we reverse the coordinates of arc 2. Why? To make the final connection correct. What I mean by final connection is that the points should start and end at the same place. So we need to have a closed loop. So this achieves that. Then the base saddle coordinates are just a list of arc 1, line 1, arc 2, line 2. The order is important. The order defines the order of connections. So if the order is missed, there will be some intermediary undesired lines, which will mess up the simulations. And then to make a numpy array out of this list, I just use the vstack function. So now, after the base saddle is created, after this line, we can go to Y gradient. So yc1 is the coil 1 of the y gradient. As we can see, the coil 1 and coil 4 are the top coils, which are defined using just simple translate of the saddle coordinates, which was the base saddle. So here I just translate it up by d over 2 and d over 2. And in z direction, I translate it by s over 2 plus l over 2, because initially my center was the origin. And then after I have my top saddles, I create the bottom ones just by simply mirroring them in xz plane. And then as we can see here, once we have the y coils in array, this array is in shape 4n3, which means we have 4 coils. Each coil has n points, and each point has 3 values or 3 coordinates. So once I have my y coils, creating the x coils is just one line, because we just rotate it in z axis, and this rotation is 90-degree rotation. So here we can see how much the rotate function simplifies our code. Then I have the list of currents. So my first 2 currents, or first 2 elements, are negative, the last 2 elements are positive. This is to achieve increasing or additive and subtractive fields. And then I just assign my currents in order to y gradient objects and x gradient objects. These objects are now Magpylib objects, and I create them using current.polyline function, and the current is the I, which is defined in this currents list, and vertices is v, and v is in y coils, which we just defined here. So here I zip the currents and y coils to just iterate over Magpy polyline object creation more effectively. Otherwise, we can just have 4 lines for each object, for each saddle. And then the same thing is done for x gradient. And after that, we get y gradient Magpy object, x gradient Magpy object, x coils, which is the coordinates, and y coils. So I return 4 of them because we'll need the Magpy objects, the gradients, for analysis, and we'll need the coils for visualization. So after we understood this function, we can run this. And then we have the create z gradient function, which just takes r and current. This is simple enough. So the distance between the coils, or the separation, is just square root of 3 times r. Here we can see that. So z1, which is the z coordinate of the top coil, is d times r over 2, and z2 is minus d times r over 2. Again, why r over 2? Because I want it to be centered around the origin. And similarly, my circle 1, which is the top coil's coordinates are just x, y, z1 stacked together, and circle 2's coordinates are x, y, z2 stacked together, and the total coordinates is a stack of circle 1 and circle 2. So this is the full coordinates of my z gradient. My up coil, which is now magnet object, is created again using by polyline function. The current is the current, and vertices is the circle 1, which was my upper coil. And similarly, I create the bottom coil Magpy object, and then I use Magpy collection function, which just combines the up coil and bottom coil and returns a single magnet, which is composed of 2 coils. So finally, I just return the z gradient, which is a Magpy object composed of 2 other Magpy objects, and coordinates, which is just a numpy array of coordinates, again in shape of n by 3. So let's run this as well. And then here we have a last function, which is just creating an axis with minimum maximum value in a desired direction. This is just needed to plot the magnetic field in a desired axis. Let's say if we want to plot it in x-axis, we'll have the blank axis populated accordingly. So similar way, we can just choose y or z axes. We'll see this being used when we will plot the magnetic field. So here we have our parameters. As we said, the resolution is hard-coded for all the functions. R is 2 meters. As we said in previous videos as well, Magpylib uses SL units. Alpha is in radians. Currently it's 2 pi over 3, which is 120 degrees. Separation is 2 meters, distance is 4 meters, the length is 5 meters, and the current is 10 amps. So here I use my create xy gradients function to get my x coil, x gradient, y coil, and y gradient, and I input my R, L, alpha, D, S, and current, which I just defined here. So let's run them. Let's see the shape of x coil. This is 4003. So here we can see y, because as we expected it would be this shape. 4 by resolution by 3, because x coil consists of 4 coils stacked on top of each other. That's why we have 4 here. So 4 coils, each coil has 4000 points. Why 4000? Because we had 2 arcs, each with 1000 points, and 2 lines, again each with 1000 points, and all of them respectively had 3 points, so 3 coordinates. Z coil was simpler. Let's run and see. The shape would be 2000 by 3. Why? Because it just was 2 coils. So here we see that. We can also define a combined coil which combines x gradient, y gradient, and z gradient. So this is combination of all coils we have. This is nice and easy way to just visualize everything on a go, like really fast. So let's run this and see. We can use the Magpylib's native show function and render it in browser and see the direction of currents and general visualization. So here we see everything matches our expectations. There is no visual errors. But for better visualization, we will use Plotly library. So we will create a figure, and in the figure we will add 4 traces for each x coil and y coil. Why 4? Because x and y gradients were composed of 4 saddles. So here I will just iterate over each saddle. And for z, it's just 1 gradient coil, which is again composed of 2 coils, but it's saved as 1. And then I define my range here. The colors are defined here. This the rest is subjective here, which can be easily changed. And this is the camera direction or position. So let's run this as well. So here we see the coils in more interactive way. Also here you can enable or disable some parts of it. So let's say we can just leave z gradient and see that, or y gradients coil 4. So as you can see, Plotly is better for more robust visualization. Now let's visualize the fields in 3D. For that I will reuse my visualize 3D function, which I used in my previous videos of solenoid, Helmholtz coil, and spherical coil. For more information, you can check those videos as well. So I will run this function. Also here I will do some trick. I will make a full coordinates array, which is again stack of x coil, y coil, and z coil. Here I do reshape to have them all n3 shape rather than 4 by n by 3. But here we just need to change this 2004 by 4000 and this by 4000. So why I am doing this step is when I define my 3D grid where I will calculate my magnetic field, there is a possibility of some small error which occurs when the grid point is really close to the current carrying coil. In that case, because the magnetic field strength is proportional to inverse of the distance square, and when the distance is less than 1, the distance square increases the field value, and we can reach singularity if we are really close. That's why we will make a threshold here and create a safe mask, let's say, or safe grid, which will ensure that we don't get too close to the coils. and our visualization is correct. For this I used the SciPy, which was imported here. So for more information you can check out SciPy, which is scientific Python library. So let's run them as well. And here I will use my visualize 3D function for Z gradient. So here we see the field is increasing with increasing Z. Here it's additive, here it's subtractive, as we were expecting. Let's run it for Y. So again, we see the result we expected. It's changing on Y direction. So similarly, we expect same behavior in X gradient. Yeah, so here we got it. So now once we ensure that our simulation and visualizations are correct, we can do some more analysis. So here I create my axes using the create axis function, which I defined here. So I create my axes of interest. So x-axis, y-axis, and z-axis. So I input x with minimum and maximum values, y and z. This minimum maximum values can be changed easily, but here I just hard coded it for ease of visualization, and we will just look for x-axis, but it would be the same for y and z-axis as well. So here I will calculate the magnetic fields of x gradient, y gradient, and z gradient by inputting the x-axis, y-axis, and z-axis, which I just defined here. And then here I define the dictionaries for multiple key and value pairs. So I have alpha parameters, which are just different values for alpha. So I have 60 degrees, 90 degrees, 120, 135, and 180, and corresponding radian values. Similarly, I created L parameters for the length, half a meter, 1 meter, 2 meter, 3 and 4, S parameters, D parameters, and R parameters. So basically I have made dictionaries for all of my global parameters here. So then what I can do, I can just iterate alpha test over my alpha parameters values, which will iterate over pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, and pi. And for each, I will create a new coil, X coil, Y coil, the gradients, using alpha test. This is important to make sure to change, because otherwise if I just put alpha here, it will just use my global alpha defined here. So if I just leave alpha, it will just do 120 degrees, which I don't want to do because I want to do parametric sweep. That's why I will make sure that I am inputting my alpha test, and I will calculate my bx gradient. Similarly, this can be done for y and z, but here I'm just doing it for x. And the name, which is the legend in the graph, would be just corresponding value of alpha test from the dictionary in alpha parameters. So let's say if the alpha test is 3 pi over 4, the name would be 135 degrees. So, and then for each iteration, I will add a line, and the name would be this. So here we see our graph, parametric sweep of variable alpha. And for example, here we can see that by increasing alpha, we get stronger fields. So I can leave only 180 degrees, and vice versa. Like the smallest alpha resulted in the weakest field. And also it's important to note that here we also lose on linearity. Linearity is also really important for gradient coils. We didn't cover it much yet, but it's important. So here we can see that 180 degrees configuration or 135 degrees configuration creates more linear curve than 60 degrees. So these two would be favored. Same way, we can run our parametric sweeps for R, and then we can do it for D, S, and L. So here are the results for D, here are the results for S, and finally here are the results for L. But so far we only did parametric sweeps for single variables, but as we discussed in the presentation, we can also do nested parametric sweeps. So for that I will have two for loops, one let's say for D and the other for S, and my title would be parametric sweep for combination of variables S and D. And it's important to note that here, unlike in previous cases, now I have two variables which are with test. So this is done in order to make sure that both D and S change with these for loop iterations. So let's run this and see the results. Here we see more curves because we have more combinations, and the same logic can be applied for any combination. You can even make more complex nested sweeps. Let's say you can iterate over L, iterate over alpha, iterate over L, R, or all variables. Or you can also make some specific condition. Let's say you can just keep the field which produced the maximum field, or you can just keep the combination which created the most linear field. So many more things can be done here. So for example, here we saw that 0.5 meter for S and 4 meter for D gave the strongest maximum field. But again, here we have some linearity issues which will need to be solved in the future. So thank you very much for your attention. The code and the links to previous videos and the resources I used will be in the description below.